Hello everyone and namaste. Swagat hai aapka in today's explainer. I am super excited to have you here today because we're about to unlock one of the coolest superpowers in mathematics. Like literally, if you've ever wondered how scientists measure massive things that they can't even physically touch, well, you are exactly in the right place. So get ready because we're going to make geometry feel like absolute magic. Let's jump straight in.
Okay, let's dive into this. On the right here, we've got a very ambitious kid trying to poke the moon with a stick. Hi, asa thodi na chand napenge. And on the left, there's someone trying to measure an entire mountain with just a super long pole. Obviously, we can't just take a giant tape measure up to the moon, right? And we clearly can't do that with Mount Everest either. So how do we actually do it? Well, we use indirect methods. And the secret math behind these indirect methods, it all boils down to one simple yet incredibly powerful geometric concept.
And that absolute superpower of a concept, it's called similarity. Now, you might remember congruency from earlier classes, right? Congruent shapes are like identical twins. They have the exact same shape and the exact same size. But similarity is slightly different. Similar figures have the exact same shape for sure, but they can be completely different sizes. It's kind of like a model car versus a real car. This one simple distinction is exactly what gives us the power to scale things up or down so we can measure literal mountains.
But hey, before we get too deep into the mechanics of it all, let me ask you a quick question. Can a circle and a square ever be similar? Like, ever? Take a second, really think about it. If you answered no, you hit the nail right on the head. No way they cannot. तो क्या आपने कभी सोचा है why that is? It's because the fundamental shape must remain exactly the same. All circles are similar to other circles. All squares are similar to other squares. But you just can't mix and match shapes and call them similar. The basic visual DNA, if you will, of the shape has to match perfectly. And this brilliantly illustrates what I like to call the Taj Mahal photo roll. Just think about a photographer printing out photos of the beautiful Taj Mahal from a single negative film. They could print a tiny little stamp-sized version, a standard passport size, or even a massive postcard size. Notice that while the line segments, like the heights of the actual walls in the photo, increase or decrease in a specific ratio, the inclinations or the angles between those lines, they always remain exactly equal. The Taj Mahal doesn't just suddenly get wider or tilted because the photo was printed bigger, right? The angles are strictly locked in. And that right there is the true essence of similarity.
So let's see how this builds with a really fun, practical experiment. Dosto, imagine karo you place a bright, lighted bulb right above a table in your classroom, and you hold a cardboard quadrilateral right in between the light and the table. What happens? It casts a shadow, right? The shadow on the table is an exact enlargement, or magnification, of the cardboard in your hand. Because light travels in straight lines, it perfectly maps the corners, the corresponding vertices, of the cardboard directly onto the table. This shadow perfectly illustrates what we call a scale factor. The shape is exactly the same, but the overall size has been magnified proportionally.
Now, what's really interesting about this slide is how we translate that intuitive, hands-on experiment into a strict mathematical rule. For any two polygons with the same number of sides to officially be considered similar, they must pass two very specific tests. Condition 1, all of their corresponding angles must be completely equal. Condition 2, all of their corresponding sides must be in the exact same ratio or proportion. If either of these conditions is missing, well, they're just non-similar shapes. You absolutely need both of them for true similarity. Which actually brings us to a true legend in the history of mathematics. Enter Thales. He was this brilliant Greek mathematician who lived way back, like over 2.5 millennia ago. Thales looked at this whole concept of similarity, specifically focusing his genius on triangles, and he discovered an absolute game-changer of a truth about equiangular triangles. Now, those are simply triangles where all the corresponding angles are perfectly equal. He realized that the ratio of any two corresponding sides in these equiangular triangles is always exactly the same. And how did he prove it? With a theorem that literally revolutionized geometry. So the crucial point is this thing called the basic proportionality theorem, also widely known as the Thales Theorem. It states that if a line is drawn parallel to one side of a triangle so that it intersects the other two sides, well, those other two sides are divided in the exact same ratio. It is so incredibly beautiful in its simplicity. Honestly, this theorem is basically the master key that unlocks complex geometry. Once you wrap your head around this ratio, you can solve almost any problem involving proportional triangles. Okay, let's break down the logic conceptually, step by step. Don't worry, we're not going to get bogged down in the heavy, messy equations here. Bahut simple. Step 1, you just draw a line parallel to the base inside your triangle. Step 2, you calculate the areas of the newly formed smaller triangles using that classic, simple half base times height formula we all know. Step 3, you find the ratio of those areas. And finally, step 4, because triangles on the same base and between the same parallel lines have equal areas, you simply equate them. Boom, you've just proved that the sides are divided proportionally. At its core, it's really just cleverly comparing areas. Easy, right? And that neat little trick leads us straight to the converse of the basic proportionality theorem. Ya coincidence nay here, guys, mathematics actually works flawlessly in reverse too. The converse simply states that if a line divides any two sides of a triangle in the exact same ratio, then that line must be parallel to the third side. It perfectly highlights how mathematical rules are just beautifully symmetrical. Think of it like this. If parallel means proportional, then proportional guarantees parallel.
Now, let's talk about efficiency, because who has time to do everything the long way? Do we always have to check all 3 angles and all 3 sides just to prove triangles are similar? I mean, that's 6 different things to measure. Thankfully, we have cheat codes. We have shortcuts like the AAA criterion. That just means if all corresponding angles are equal, boom, the triangles are automatically similar. Or there's the RHS similarity criterion for right-angle triangles. These shortcuts save us so much time. They're exactly what allow engineers and scientists to quickly prove similarity and measure massive things out there in the real world that they can't physically reach.
We have covered some seriously amazing ground in this explainer today. I mean, we went from kids poking sticks at the moon to Thales entirely revolutionizing math. So I want to leave you with a little challenge. Next time you're walking outside and you look up at a giant building, or maybe a really tall tree, ask yourself, how will you measure its height using just your own shadow, a tape measure for the ground, and this awesome concept of similarity? Because you now have the mathematical superpower to actually do it. Think about it, try it out, and keep exploring the magic of geometry. Thank you so much for joining me today, and I will see you next time.